Python 3.14 is a broad release rather than a single headline feature. It changes how annotations are evaluated, introduces template strings, makes free-threaded CPython officially supported, exposes multiple interpreters in the standard library, and adds practical tools for compression, debugging, and migration. This series begins with changes every Python developer can use, then advances into concurrency, runtime architecture, extension compatibility, and deployment. The discussion reflects the Python 3.14.7 documentation current on August 7, 2026, including maintenance line corrections after the original 3.14.0 release. This chapter focuses on the parts of Python 3.14 that change everyday authoring. Deferred annotations reduce import time work and remove many awkward quoted forward references. Template strings preserve interpolations for custom processing rather than immediately producing text. Smaller syntax and diagnostic changes make exception handling and debugging clearer. The goal is not only to recognize the new syntax, but to understand when it changes runtime behavior, which introspection patterns deserve testing, and where new flexibility still requires a deliberately safe processor. Python 3.14.0 was released on October 7, 2025. By the date of this series, 3.14.7 is the current maintenance release, so the practical target is not the original 0.0 build. That distinction matters because maintenance releases can correct implementation choices while preserving the feature version. The most visible example is garbage collection. The incremental collector used in 3.14.0 through 3.14.4 was reverted in 3.14.5. For application planning, treat Python 3.14 as a maintained release family and test against the newest available point release. Python 3.14 changes authoring along three related dimensions. First, annotations are no longer evaluated when a function, class, or module is defined, unless the older future import behavior is requested. Second, a template string produces a structured template object rather than a finished string, giving a trusted processor control over every interpolation. Third, several smaller improvements tighten the feedback loop. Clearer syntax errors, a warning for control flow that escapes a finally block, optional parentheses in multi-exception handlers, and color in the interactive shell and several command line tools. Before Python 3.14, an annotation normally executed while its definition was created. A name that had not yet been bound therefore raised an error unless it was written as a string, or the annotation's future import was active. Under the new default, CPython stores a generated annotation function and evaluates it only when annotation values are requested. This makes natural forward references possible and reduces work during imports. It does not mean every annotation can always resolve. Requesting a value can still raise name error if the reference name remains unavailable at evaluation time. The new AnnotationLib module makes the evaluation policy explicit. Value format is closest to the historical behavior of reading evaluated annotations, so it can execute annotation expressions and fail on missing names. FORWARDREF format evaluates what it can and substitutes forward ref objects for unresolved names, which is useful to frameworks building type graphs. String format produces source-like text and avoids resolving names. Library authors should choose the least powerful format that satisfies their use case. That decision improves predictability and reduces accidental execution during schema, routing, validation, or documentation discovery. The majority of applications can adopt deferred annotations without source changes. The higher risk category is code that treats annotations as active runtime configuration. Decorators, metaclasses, dependency injection systems, serializers, and documentation tools may read annotations at definition or import time, and may assume exact object or string forms. Test those paths with representative forward references and aliases. The future import remains meaningful in 3.14. Code using it continues to store annotations as strings. Removing it is therefore a separate migration decision, not a mechanical cleanup required for this release. An F string commits immediately to a string. A T string uses similar braces, but returns a string.templatLib.template object containing static strings and interpolation objects. The interpolation stores the evaluated value together with the expression text, conversion, and format specification. That structure creates a boundary where a processor can make domain-specific decisions. A processor may escape text for hypertext markup language, bind values to a database operation, generate structured logging fields, or return a document object model rather than text. The T-string itself does not provide safety. The processor supplies the policy. This simplified renderer demonstrates the important architecture. Callers author a template, while one trusted function decides how interpolated values enter the output. Static text passes through. Values are escaped before joining. A production hypertext markup language processor would also account for attribute, URL, script, and style contexts rather than applying one universal rule. The same principle applies to structured query language and shell operations. A processor should use parameter binding or argument arrays, not merely quote text. Template strings make a safe design easier to express, but the safety property still belongs to the processor implementation and its tests. Template strings are most valuable, where converting to plain text too early destroys information. Web renderers can distinguish trusted markup from values. Database adapters can produce a query plus bound parameters. Logging systems can keep structured fields for filtering, privacy controls, and later formatting. Domain-specific languages can validate values against a grammar or type system. The common rule is to preserve structure until a trusted boundary with a clear contract. If a processor immediately joins every part with str, it may provide convenience, but captures little of the design advantage and may recreate the same injection risks as ordinary concatenation. Python 3.14 allows the parentheses around multiple exception types to be omitted when there is no as clause. The original parenthesized form remains valid and may still be preferable when formatting a long set of types. The restriction around as avoids ambiguity. When binding the exception object, keep the exception tuple parenthesized. This is a readability change rather than a new exception model. Teams should let their formatter and style guide settle the preferred layout instead of launching a broad mechanical rewrite. The useful takeaway is that the grammar now matches the way many developers naturally tried to write this handler. A return, break, or continue that exits a finally block can replace an earlier return value or suppress an exception that was already in flight. Python 3.14 makes this visible by emitting syntax warning during compilation. CPython still accepts the construct in this release, so the warning is a migration signal rather than a universal syntax error. Fixing it usually means keeping cleanup in finally and moving outcome selection after the try statement, or using an except branch for fallback behavior. Enable warnings in continuous integration so these patterns are found before a later Python implementation or release chooses stricter enforcement. Python's parser now recognizes more common intent patterns. A keyword typo can suggest the intended keyword, an elif after else receives a specific ordering message, and invalid statement placement in a conditional expression highlights the actual requirement. Type errors for unhashable values also explain whether the object was being used as a dictionary key or set element. These messages are especially helpful to learners, but experienced developers benefit as well because diagnosis begins closer to the cause. Tooling that snapshots exact error text should avoid brittle full-string assertions when a stable exception type and a focused substring are sufficient. The default interactive shell now highlights Python syntax using a conservative terminal palette. Color also appears in several standard library command line interfaces, including argparse_help, unit_test, JSON, calendar, and the debugger. This is more than decoration when scanning a traceback, command help, or source listing during an incident. At the same time, automation must not depend on color codes. Python follows common environment controls for disabling color, and the basic interactive shell can be selected when compatibility matters. Treat colored output as a human interface enhancement and keep machine consumption on structured data or explicitly uncolored output. The adoption pattern differs by feature. Deferred annotations are the new default, but the work is in validating runtime consumers rather than rewriting all hints. Template strings deserve targeted adoption, where a processor can enforce a useful boundary. They should not replace f-strings indiscriminately. Parentheses-free exception lists are purely stylistic. The finally warning should be treated as a defect because hidden exception suppression is rarely intentional. Color can be enabled for people and disabled for machines. A sensible migration, therefore, combines broad interpreter testing with narrow, high-value source changes instead of equating a version upgrade with a syntax modernization campaign. These official documents separate the implemented behavior from the design rationale. The What's New guide is the best current overview because it is updated along the maintenance line. The individual Python enhancement proposals explain why deferred annotations, template strings, exception grammar, and finally warnings were designed as they were. The release schedule establishes support timing, while the current release page confirms the latest maintenance build. When a proposal and the maintained documentation differ in operational detail, prefer the current documentation for behavior, and use the proposal to understand goals and trade-offs. The language story in Python 3.14 is coherent. Deferred annotations postpone work and preserve the possibility of different representations. Template strings postpone rendering and preserve the boundary between static text and interpolated values. Diagnostics move in the opposite direction by surfacing likely intent and risky control flow earlier. The practical response is to preserve structure where it creates leverage evaluate only with an explicit policy, and promote warnings into the development workflow. The next chapter applies the same themes of explicit boundaries and controlled sharing to threads, isolated interpreters, runtime performance, and production observability. Python 3.14 expands the concurrency design space. The free-threaded build advances from experimental to officially supported, while remaining optional. Multiple isolated interpreters become accessible through the standard library and provide another route to multi-core parallelism. These are distinct models with different sharing, compatibility, and operational costs. The release also adds an opting tail call interpreter, a safe external debugger interface, and tools for inspecting asynchronous task graphs. This chapter compares the models directly and includes the important maintenance update that changed garbage collection after 3.14.0. The Global Interpreter Lock, or GIL, is still present in the standard CPython build and remains appropriate for many applications, especially input-output concurrency. The free-threaded build removes that lock so multiple threads can execute Python bytecode in parallel. But shared mutable state now demands more disciplined synchronization, and every native dependency must be compatible. Isolated interpreters take a different approach. Each interpreter has its own modules, classes, functions, and variables, with communication occurring through defined channels or serialization. Choosing among them is an architectural decision about sharing and isolation, not merely a performance switch. Python 3.14 moves free-threaded CPython into Phase 2 of the plan established for making the GIL optional. Supported status signals that the design and application programming interfaces are stable enough for real use and ecosystem adoption. It does not change the default interpreter and does not promise that every package is ready. It also does not make operations on a complex shared object automatically atomic or application invariants automatically safe. Teams should treat the build as a supported deployment target that requires dependency qualification, concurrency design, and workload-specific measurement. Free-threaded mode is a trade. Python 3.14 documentation reports roughly 5 to 10% lower single-thread performance than the conventional build, depending on platform and compiler. In exchange, well-designed central processing unit-bound threads can use multiple cores without the GIL serializing bytecode execution. Real scaling is limited by contention, memory bandwidth, task granularity, and native code. A service dominated by one request thread may pay overhead without receiving throughput. A batch workload with independent tasks may gain substantially. Benchmark latency, throughput, memory use, and tail behavior using production-like dependencies before selecting a runtime. Free-threaded readiness is an end-to-end property. A native extension must declare support and protect its own mutable state without assuming that the GIL provides serialization. When an incompatible extension is imported, CPython may re-enable the GIL to preserve safety, which changes the performance model even if the main application is thread-safe. Inventory direct and transitive native dependencies confirm that free-threaded wheels exist for the target operating system and verify at runtime whether the GIL is active. On Windows, build backends must explicitly define the py_GIL_disabled preprocessor variable when compiling extensions for the free-threaded build. Removing the GIL does not remove data races. Even if an individual container method has internal safety, an application invariant spanning a read and a write can be interrupted by another thread. The counter protects the entire update and read operations with one lock. More scalable designs often avoid shared mutation entirely by partitioning state, sending immutable messages, or assigning one owner to each resource. Locks should protect the smallest coherent invariant, but making them too fine-grained can introduce deadlocks and overhead. Correctness tests should include stress, cancellation, shutdown, and error paths, while performance tests should reveal contention under realistic worker counts. CPython has supported multiple interpreters internally for decades, but Python 3.14 makes them accessible through the concurrent.interpreters module and interpreter pool executor. Each interpreter owns its own sys.modules, classes, functions, and most runtime state. Because interpreters have separate locks, they can run Python code in parallel inside one operating system process. Isolation changes the programming model. Ordinary objects are not shared across interpreters, so values are copied, serialized, or transferred through supported mechanisms. This resembles processes conceptually, but can use fewer system resources and avoids a separate process boundary. Interpreter Pool Executor extends the concurrent futures model with interpreter isolation. It is attractive for central processing unit-bound functions that accept and return transferable values. The example is intentionally simple. A top-level function maps cleanly across workers. Real applications must account for per-interpreter imports, initialization, serialization cost, and extension compatibility. Objects are not ordinary shared references, so code that relies on module-level caches or open client instances needs a worker setup strategy. Compare this executor with process pool executor using the actual payload size and task duration. Lower isolation overhead does not guarantee a win for every workload. The first standard library release of interpreters exposes real limitations. Startup has not yet been optimized, and each interpreter uses more memory than the long-term design intends. Cross-interpreter sharing is deliberately narrow, so serialization can become a significant part of total cost. Native extensions must isolate their module state, and many ecosystem packages are still adapting. These limitations do not make the model unusable. They define the workloads most likely to benefit. Prefer coarse, independent tasks with modest inputs, substantial computation, reusable workers, and a dependency set already verified for isolated interpreters. Start concurrency selection with state, not worker syntax. Asyncio is effective when many operations wait on input-output, and tasks can cooperate within one interpreter. Conventional threads integrate blocking libraries and share objects conveniently, but the GIL limits Python bytecode parallelism. Free-threaded Python adds parallel bytecode while retaining shared memory, increasing synchronization responsibility. Interpreters provide multi-core execution with isolation inside one process, while processes offer the strongest mature boundary at higher operating system and transfer cost. Prototypes should measure realistic task size, cancellation behavior, failure isolation, startup, memory, and dependency compatibility. Python 3.14 includes an alternative bytecode interpreter that uses tail calls between small c functions implementing opcodes. On supported architectures with Clang 19 or newer, preliminary PyPerformance results show a geometric mean improvement of roughly 3 to 5%. This is an internal implementation strategy and does not add tail call optimization to Python functions. It is opt-in when building CPython from source, and profile-guided optimization is strongly recommended. Because the gain depends on compiler, architecture, build flags, and workload, treat the published number as a reason to benchmark rather than a guaranteed application improvement. The Safe External Debugger interface lets a tool ask a running CPython process to execute a file at the next safe execution point. Unlike always-on tracing, the normal path carries no continuous runtime overhead. The sys remote_exec convenience function exposes the mechanism, while tool authors can implement the protocol directly. This capability is powerful enough to require an explicit security posture. Operators can disable it through python_disable_remote_debug, a command line option, or a configure time build flag. Access to attach should be governed like other privileged debugging facilities, with operating system permissions, audited tooling, trusted script paths, and minimal production exposure. Python 3.14 adds both command line and in-process tools for understanding asynchronous execution. The PS command lists tasks, coroutine stacks, and awaiter relationships for a running process identifier. The PS tree command organizes the same information into a hierarchy, which makes stuck branches and unexpectedly long dependency chains easier to spot. Capture_call_graph and print_call_graph expose related information inside an application. These tools complement, rather than replace, metrics and distributed tracing. A task graph explains local control flow at one moment, while production observability still needs timing, request identity, resource usage, and cross-service context. Global warning filters are difficult to reason about when multiple threads or asynchronous tasks enter catch_warnings at the same time. Python 3.14 can store warning state in a context variable, providing predictable isolation across concurrent work. The context_warnings option defaults on in the free-threaded build and off in the conventional build. A related thread_inherit_context option controls whether a new thread begins with a copy of its caller's context, with the same build-dependent defaults. Because behavior can differ between builds, test warning-sensitive libraries under both configurations and set flags explicitly when consistency matters more than preserving defaults. Python 3.14.0 introduced an incremental cycle collector intended to reduce maximum pause times on large heaps. Production reports then identified significant memory pressure, and Python 3.14.5 reverted the change to the generational collector used in 3.13. Current 3.14.7 documentation presents the reverted behavior as the active state of the series. This is a valuable release engineering lesson. Benchmark and operational guidance must name a point release when maintenance updates materially change runtime behavior. Remove assumptions tied to the temporary incremental collector and validate memory, pauses, and explicit GC module calls on the exact build deployed. The maintained What's New guide is essential for this chapter because it records the garbage collector reversion and the current free-threaded performance description. The free-threading proposals distinguish the long-term plan from the specific supported status decision in Python 3.14. The multiple interpreters proposal and standard library documentation describe both isolation guarantees and present limitations. The external debugger proposal explains the security and execution model behind remote attachment. Use these sources together. Proposals provide rationale, while the current library and release documentation define the behavior that applications should test. Python 3.14 does not replace one concurrency model with another. It adds credible options. Free threading favors shared memory threads and rewards careful synchronization, compatible extensions, and scalable task design. Interpreters favor isolated state and explicit communication, trading easy object sharing for a clearer boundary. Conventional threads, asyncio, and processes remain valuable. The runtime decision should include more than throughput, evaluate memory, initialization, failure containment, deployability, debugging access, and asynchronous observability. The final chapter turns from runtime architecture to the standard library, platforms, C integration, removed interfaces, and a practical upgrade sequence. The final chapter turns Python 3.14 into an upgrade plan. Several new modules provide substantial capability without third-party dependencies, led by Zstandard compression, annotation inspection, template support, and interpreters. Existing modules gain modern identifiers, friendlier command line behavior, asynchronous debugging, and better syntax tree tools. Platform coverage expands to official Android binaries and Tier 3 mscripting support. At the expert end, embedders receive a new configuration application programming interface, and extension authors face limited interface changes. The chapter closes with removals, release integrity changes, and a staged migration workflow. Python 3.14 adds 4 important library areas. Annotation lib gives runtime consumers a supported interface to deferred annotations. The compression package groups the existing gzip, bz2, lzma, and zlib interfaces under preferred names and adds Zstandard. Concurrent.interpreters expose these isolated interpreters to Python code. String.templatelib defines the objects produced by template strings. These modules align with the release's larger theme, preserve structure, and expose explicit control. Existing top-level compression imports are not deprecated in 3.14, so adoption of the new namespace can be gradual and compatibility-driven. The compression. ZSTD module exposes Zstandard compression and decompression through standard library bindings. Its programming model is intentionally familiar to users of gzip, bz2, and lzma, with both one-shot and streaming operations. Bringing the format into Python reduces dependency cost for archives, data pipelines, caches, and network tooling that already exchange Zstandard data. Adoption should still include interoperability tests for framing, dictionaries, compression levels, and streaming boundaries. A built-in module simplifies availability. It does not choose the right speed, ratio, memory, or compatibility settings for a particular protocol. Zstandard support is integrated into tarfile, zipfile, and shutil, so applications do not have to drop to a low-level codec for common archive workflows. This is most useful when an archive format and its downstream consumers already agree on Zstandard. Changing a default compression format is a compatibility decision. Deployment tools, operating system utilities, older Python versions, and partner systems may not recognize it. A safe rollout publishes format metadata, maintains a fallback where necessary, and measures both producer cost and consumer latency. The legacy gzip, bz2, lzma, and zlib module names remain available. Python 3.14 implements the newer identifier formats standardized in Request for Comments 9562. Version 6 reorganizes version 1 style timestamp fields for improved sorting. Version 7 combines Unix epoch milliseconds with random bits and is often the best default when new identifiers should roughly follow creation time. Version 8 reserves a layout for coordinated application-specific schemes and should not be treated as an invitation to invent incompatible formats casually. The module also exposes NIL and MAX Sentinel values. Time ordering can improve index locality, but identifiers still need clear privacy, collision, and clock behavior analysis. The UUID module now provides UUID 6, UUID 7, and UUID 8 constructors. A version 7 identifier includes a millisecond timestamp that is available through the time attribute, making chronological sorting and partitioning straightforward. That timestamp also exposes approximate creation time, which may be undesirable in a public identifier. Version 8 accepts custom fields and therefore demands a documented organization-wide format if it is used at all. Before migration, verify database types, validators, regular expressions, application programming interfaces, and language implementations across every service. An identifier can be valid under the new standard, while still being rejected by older assumptions. Argument parser gains suggest underscore on underscore error for close matches to choices and subparser names, while colored help improves interactive readability. These features can upgrade a command line experience with minimal code. They also reinforce a boundary between human and machine interfaces. A script should use exit status, a documented structured output option, or a stable protocol rather than parse colored help and error prose. If tests compare output exactly, set color explicitly, or disable it through the standard environment controls. Suggestions are guidance, not fuzzy acceptance. The parser still rejects an invalid value, preserving deterministic command behavior. Abstract syntax tree, or AST, tooling receives several improvements. AST.compare can determine whether two trees are structurally equivalent, which is useful in refactoring tests and compiler tooling. AST nodes support copy.replace, allowing a modified node to be created through a shared replacement pattern. Their repr output includes more information, and the AST command line adds options for feature version, optimization, and empty fields. Tools should still avoid constructing invalid trees, or depending on unstable representation details. Prefer semantic comparisons and explicit fields over snapshotting an entire repr when compatibility across Python versions matters. pdb.set_trace_async adds a debugger entry point designed for coroutine code, including support for await while stopped. Source listings can also be syntax highlighted. Together with remote attachment and asyncio task graph inspection, the standard library now covers more of the debugging lifecycle, entering a specific coroutine, reading the local source clearly, attaching to a live process, and understanding how tasks await one another. Production use still needs operational safeguards, and asynchronous debugging can perturb timing. Reproduce a failure with tracing and structured logs when possible, then use an interactive debugger to answer a focused question. Python 3.14 contains many focused library changes. Pickle Protocol 5 becomes the default, and error notes can identify where serialization failed. Regular expressions accept \z as an unambiguous end-of-string marker, while \b now behaves as the logical opposite of a word boundary even for empty input. The struct module adds complex floating formats matching C types. Hash-based message authentication code, or HMAC, gains a built-in implementation based on formally verified HACL star code. Each change is small, but exact output tests, stored serialized data, and cross-language protocols should be exercised during an upgrade. Platform support expands in several directions. Python.org now publishes Android binaries, giving mobile toolchains an official upstream build. The Emscripten WebAssembly target becomes a Tier 3 platform and gains broader module support after significant work in the surrounding C library. Official Windows and macOS binaries can support the experimental just-in-time compiler, though experimental status calls for conservative deployment. CPython builds also enable recommended compiler safety options by default, with configure switches for different trade-offs. Platform support tiers describe upstream commitments. Application dependencies and packaging tools still require their own qualification on each target. Python Enhancement Proposal 741 adds PyInitConfig, a configuration layer for embedders that avoids exposing a C structure whose layout constrains future binary compatibility. Options are set and queried by name, and initialization can include built-in extension modules. The slide shows the intended sequence rather than a complete production error handling implementation. Embedders that emulate the full CPython command line may still need the lower-level PyConfig interface from Python Enhancement Proposal 587. Migration should identify which configuration behaviors are truly required, build an explicit option map, and test initialization, finalization, isolation, module registration, and error reporting across supported Python versions. The limited C application programming interface continues moving toward opacity. In its Python 3.14 form, py_type and py_refcnt are implemented as calls rather than direct structure access, and broken pysequence_fast macros are removed from the limited interface. Free-threaded execution also weakens assumptions based on a reference count of 1. New unstable helpers exist for specific uniqueness questions. Extension authors should separate code using the stable or limited interface from implementation-specific fast paths, compile with strict warnings, run reference and free-threaded builds, and test multiple interpreters. Direct access that works today can undermine both compatibility and thread safety. Python 3.14 removes interfaces that have carried deprecation warnings across earlier releases. Representative examples include old abstract syntax tree constant aliases, legacy event loop patterns, pk-gutil loader helpers, obsolete pseudo-terminal functions, SQLite 3-module version names, and historic URL opener classes. The risk often sits in a transitive dependency rather than application code. Run the test suite on the newest Python 3.13 with deprecation warnings visible before switching versions, because that environment can reveal many removals while the old runtime still works. Then test Python 3.14 and distinguish genuine compatibility failures from intentional changes in exact output or diagnostics. Begin with an inventory of Python runtimes, operating systems, native extensions, build backends, and code that touches removed interfaces. Next, run the current Python 3.13 test suite with deprecation and syntax warnings visible. Fixing those signals reduces uncertainty before the version change. Add the newest Python 3.14 release to continuous integration. Then stage representative data, concurrency, packaging, and embedding scenarios. A production canary should have explicit rollback criteria for errors, latency, memory, and dependency behavior. Once compatibility is stable, adopt new language features in focused changes so regressions remain attributable. Python Enhancement Proposal 761 discontinues pretty good privacy signatures for official CPython releases, largely because the workflow provided limited practical assurance and imposed maintenance cost. Organizations with download automation must update explicitly. A missing signature should not cause the pipeline to fall through to an unverified install. Use the verification information supported by the official release channel. Pin trusted origins, record the artifact hash, and follow current packaging guidance for provenance. The exact enterprise control depends on the distribution path, but the principle is stable. Make verification observable, fail closed when expected evidence is absent, and review the supply chain as a system. A production upgrade is complete when the evidence is retained, not when the interpreter starts. Application tests should cover behavior and warnings. Dependency evidence should prove that approved wheels exist for every platform, especially for free-threaded or isolated interpreter use. Data tests should exercise stored pickles, compression formats, identifiers, database drivers, and cross-service validators. Operational testing should capture memory, garbage collection behavior, debugger controls, styled command output, and rollback. Embedders and extension authors need additional initialization and application binary interface coverage. Assign an owner to each domain and keep the result with the release decision. The maintained what's new and porting sections are the primary migration references because they consolidate library changes, removals, deprecations, C interface updates, and point release notes. The Zstandard, configuration, platform, and release integrity proposals provide deeper rationale and specifications. The UUID library documentation defines the exact constructors and properties used by the newer identifier versions. The current release page confirms the maintenance target. Pair these references with the documentation for every affected dependency. Python's standard library compatibility does not establish that a framework, native extension, or deployment tool supports the same target. Python 3.14 is a substantial, mature feature line. Its value is not measured by how many new constructs appear in a code review. The strongest adoption choices are specific. Deferred annotations, simplify definitions, and give consumers explicit formats. Template strings create enforceable processing boundaries. Free threading and interpreters expand parallel design. Zstandard and newer identifiers remove common gaps, and improved tools shorten diagnosis. A responsible rollout targets the latest point release, tests the full dependency and data path, records operational evidence, and introduces optional modernization in focused increments. That approach captures the release's benefits while keeping causality, rollback, and long-term maintenance clear.